Welcome to iLecture Online, and here's another example of how you can apply electrical potential and electrical potential energy to some interesting problems. So let's take a look at this one. It says here that an alpha particle with kinetic energy equal to 11 million electron volts, 11 MeV as we call it, that is directed to a lead nucleus. How close will it get before the alpha particle is completely stopped? The reason why I picked this one is for several reasons. One is that I like to give you some familiarity what we mean by electron volts and million electron volts, and to give you kind of a feel for a very interesting and practical problem that involves nuclei and nuclear pieces moving towards each other at very high velocities, and then seeing how the repulsive forces between the positive charges within the nucleus of the lead nucleus and the nucleus of the alpha particle, how they will repel each other probably before they actually will meet. So let's draw a little picture of that. So here we have an alpha particle. Now, if you're not sure what an alpha particle is, it is the nucleus of a helium atom, which means it has 2 protons and 2 neutrons. So it kind of has like 4 nuclear particles, and it's speeding very fast with some very high velocity towards a big nucleus of a lead atom. And a lead atom has 82 protons in it, so 82 positive charges, where an alpha particle has 2 positive charges. It also has a bunch of neutrons, but we can ignore the neutrons. And assuming that the lead nucleus will not move, it will just stay in place. Okay, so the alpha particle has a kinetic energy equal to 11 MeV, which is the same as saying 11 million electron volts. 11 with 6 zeros electron volts. So what is an electron volt? It's a unit of energy. It's the energy required to push a single electron or a single proton, a single charge across a potential difference of 1 volt. So if we say we have, for example, a difference of 1 volt between these 2 plates, and you take a proton and you push it across all the way across a potential difference of 1 volt, it will require the work equal to 1 electron volt. And when it then gets to the other side, assuming that this side is positive and this side is negative, when you get that proton to the other side of that 1 volt gap, you now will have given it the potential energy of 1 electron volt. So that's what an electron volt is. If you want to convert electron volts to joules, 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So that's how we convert to the standard units. All right, knowing that, how do we now solve the problem? Well, we can assume that at some point, not quite where the lead nucleus is, at some distance r away from the nucleus, which is what we're looking for, how close will it get, the kinetic energy will have been completely converted into potential energy, and the alpha particle will simply stop at that point, and then repulsive forces will push it back. So it's a situation of the initial energy equaling the final energy, and the initial energy would be the kinetic energy of the alpha particle, and then the final energy would be the potential energy it has when it gets there. So the kinetic energy initially has been given to us in terms of electron volts. We simply have to convert it to joules. The final potential energy is going to be the potential energy of the system, which can be calculated, the potential energy final, which can be calculated by taking the volts or the potential at that location due to the charge of the lead nucleus times the charge that we place there, which in this case would be the alpha particle. So the potential energy is going to be K times Q of the lead nucleus. I'll just put sub PB there, divided by the radius that we're looking for. So that's the voltage or the potential at that location, and then we multiply that times the charge, Q of the alpha particle, and that will give us the potential at that location, or the potential energy, I should say potential, but the potential energy at that location. So plugging that into the equation, we can then say that the initial kinetic energy is equal to K Q of the lead times Q of the alpha particle divided by the distance between them. And since that's what I'm looking for, I'm going to solve this equation for R, place it over here. So the distance R is going to be equal to K times Q of the lead times q of the alpha particle, all divided by the kinetic energy that it has initially. All right. Now, let's plug in the numbers. So K is equal to 9 times 10 to the 9th newtons meters squared per coulomb squared. The charge of the lead nucleus, now there's 82 protons, so it's 82 times the charge of a single proton, which is 1.6 times 10 to the minus 19 coulombs, times the charge of the alpha particle. Now it has 2 protons, so it will be 2 times 1.6 times 10 to the minus 19 coulombs. And then we take the whole thing and divide it by the kinetic energy, which we said was 11 times 10 to the 6th EVs. But of course, we don't want to leave it in EVs. We want to convert it to joules. So that means we have to multiply this times the conversion factor of joules to electron volts. 1 electron volt is 1.6 times 10 to the minus 19 joules. Now notice that we have 1.6 times 10 to the minus 19 up here and 1.6 times 10 to the minus 19 there. The coulomb squared cancels out the coulombs and the coulombs, and the electron volts are canceled out. And so we have Newton meters squared divided by joules, and that ends up being meters, believe it or not, because Newton meters is joules, so that cancels out one of those and one of those, and so the whole thing ends up in meters. So now we need a calculator to figure out what that number is. Wonder how close they get. That's the excitement of doing physics. You get to kind of wonder about these things and actually figure out what they are. So let's see. 9e to the 9th times 82 times 2 times 1.6 exponent 19 minus, divide that by 11 million. And then that's it, because I have everything else. All right. And what do I get? Ooh, that's pretty close. 2.1 or 2.15 times 10 to the minus 14 meters. And since the nuclear radius is about 1 times 10 to the minus 15 meters, it gets to within 10 to 20 nuclear radii away from the lead nucleus. So this is probably not a good representation. It would be maybe about 10 times the size of the lead nucleus, but hey, that gives you a pretty good idea of how close these things get. 11 million electron volts is a lot of energy, but yet the repulsive force will stop it in its tracks and push it back away. And that's how you do a problem like that. Okay, hope you enjoyed this one, as much as you can enjoy physics, I suppose. And if you're still a little confused, let me come up with another example to help you understand how to do these types of problems. All right.